Okay,
Okay,
we are recording. This
cool.
is Gina Bernardini. This is Greg Perkins as our guest, and I'm Santiago Echeverry. And Gina is going to be presenting her senior project in mathematical programming, which is a joy. We need to be aware that Gina is a dual major in animation and mathematical programming. So, Gina, this is all yours, and please let us know about your presentation.
Okay, thank you. So today I'm going to be talking about mathematical simulations in 3D animation. So I'm doing kind of a marriage of my two degrees, two things that I really love. So I'm super excited about this presentation. And I hope it'll help people understand a little bit more about what goes into some really popular films and cool stuff that they just don't understand. So an overview of what I'm going to be talking about. So what are simulations? What are they in animation? Why are they used? And then the majority I'm going to be spending on character simulation. So that's clothing and hair. There are a lot of other types of character simulation, but that's mostly what I'm going to be talking about. And overall, I'm going to be creating a simple interactive 3D curtain. So it's going to be kind of a mixture between a clothing and a hair simulation. Um, in 3D. So here's a simple, example of a simulation in 3D that most people wouldn't expect. This is a big one. This was a huge challenge for Pixar. They made kind of a mini docuseries on it, which is why I have a lot of background information about this specific case. So Merida is from Brave. She has the big curly hair. So a lot of her hair sections are parted into these springs, which was a big challenge because it has to interact with the way that she moves. So that's why character simulations are so unique, because they have to follow the physics of the character also, in addition to the physics of the world that you're creating in 3D. So we're seeing here these springs that make up her hair. It's super cool. So I'll be going into a little bit more detail on that. So just categories of simulation that are pretty common in 3D animation. So particle system special effects, that's going to be the first one that everyone thinks of. That's where we're assigning particles. They're just small objects in the scene, some attributes that would make them look like, say, water, smoke, or fire. In the case of water, it could be reflectivity or other attributes, and then giving those particles equations to react to in the scene that would make them reminiscent of those special effects. So that can be used in 3D animation. That can also be integrated into live action film, special effects, any things like that. It's the same math, same things apply. Character effects, so that's what I'm going to be talking about today. So that's clothing and hair. I'll go into more detail on that. Lighting and shading is a big one that people forget about. So not all of the shadows and lights are hand drawn in these films. So the computers understand in the scenes where the lights are coming from, the vectors of the actual light, how strong they are, those kinds of things. And then they're going to pick up on the actual attributes of the objects in the scene. So that's like the reflectivity, that's the specular effects. So then it's going to bounce off of those other objects and create these extra shadows. So that's all simulation, and that's all coded by lighting artists, which is really cool. And then another big one is crowds and combinatorics. So I'm going to talk about efficiency in a little bit, which is a big reason for simulation, but that's the main reason behind crowds and combinatorics. So crowd scenes are very taxing on animators. So you can do combinations of animations to put together, and the computer will do it for you. Same thing goes for modeling. So here is a case of some animators or some modelers setting different clothing colors, different heights, different skin colors, gender, things like that, hair length, hair type, and putting them all into a bank. And then the program will create these models on their own, and generate them from the parts that were given, so that the artists don't have to go through and create each individual character. It saves a lot of time. So that's a big one too. So here's a few pictures of examples. So this one is really cool. This is from Frozen. We're seeing some vector particles here. This is wind moving through the scene. And then we're also seeing some character effects of her hair and this cloth, her dress, reacting to the wind that they've placed in the scene here. So they actually can visually see that. It's, in the film, it's implied, you can't really see wind, but that's how that's represented. Top right is a clothing simulation. So that's just how this piece of cloth is interacting with the solid object underneath it. So it's being draped around that object. There's some collision there, so that this piece of cloth can't fall through. It's going to lay right on the tangents of all of the vertices of the underlying like solid object. So this bottom left is Sully without hair. It's a little weird, but you can't draw or animate every piece of fur and hair. So it's the same thing as the other hair up here, but it's all over. So they're going to assign sections where those hairs are going to go, how many hairs in each section, different things like that, set the physics for them so that each character is a little bit unique. And then down here is another example of a particle system. A lot of people just assume that it's water and things like that. Anything can be a particle and anything can be put into those systems. So in this case, it's those the petals from the flowers that they're using in the Day of the Dead celebration in Coco. So when he strums the guitar, there's like that wind, that gust of wind that comes up, and those petals go all over the place. So the attributes set to those particles are to look like those individual petals, and those are what are going through the program and going through that simulation. So what kind of math goes into simulations? All kinds of math. This simulations, like I said, that was only a few of them, expand through everything. But today I'm going to primarily be discussing algebra, some geometry, and then discrete mathematics, because we're going to be talking about a little bit of coding. So where is the math? Here's where I'm just going to briefly mention code in the beginning, is that in all of these cases, all of these objects, all of these, the motion is being generated by the computer. So you have to communicate with the computer. You're creating everything here. So you create the environment that you want. In these systems, you do not have to follow the conventional laws of physics. You're inventing your own scene. So even elements like gravity, you can change how gravity affects different objects so that they look different in the scene. This will play out for entertainment purposes, for anything like that. So here we're using math to communicate with the computer. The computer has to understand ultimately in all of these cases where these vertices are of all of these objects, where these particles are going, all those things like that. So this is where we're talking about position, velocity, all that stuff, acceleration. So the computer can predict where these objects going to go, what is the motion going to look like. But that's actually the really cool thing about simulation, is you can make anything happen because it doesn't have to follow conventional physics and conventional rules of our world. So here's another example of where I'm going to be talking about math. So geometry, we're talking about the topologies of models. So that's just the layout of the vertices and faces that make up a character in 3D space. So this is Miles Morales from Into the Spider-Verse. This is a little close up on his eye. Those neon shapes are the controllers of his rig. So that's how the animators would control those vertices. But each one of those panels, the faces can move. Those are the values, those points that the computer is going to be using to execute these simulations. So each one of those particles in space X, Y, and Z the values are stored where they are in the 3D space. So the computer is actually, here I wrote that it takes a lot of power. It's very taxing. This is a reason why we can't do it ourselves. So the computer, you can set your intervals on what time you need the computer to be understanding where these points are. In animation, a lot of times it's 24 frames per second, but it can be much less fractions of a second, many more. And especially in simulation, the computer is constantly trying to understand where these points are in the 3D space, computing these positions and storing them, and repeating the equations over and over and over again. So this is a reason why we can't do these ourselves. But so this is where the math of the geometry is, how these points interact with each other, and so on. So I'll go into that a little bit later also. So why do we use these simulations? I mentioned efficiency briefly. In 2D animation, of course, that's like stylistic. You can do that, it has the same effect, but you'd have to hand draw each one of these effects. It takes a long time. It's not always accurate, that kind of stuff. In cases like combinatorics, it's simply for efficiency. The animators and the modelers can do the animation, they can create those models, but in the interest of time, in the interest of a production, this is going to save a lot of time. So creating crowds and preventing character models from creating hundreds of different characters. A great example of that was Monsters University. They're all these monsters. They're crazy shapes, crazy colors. How could you invent that many different monsters? If you tried to sit and design one character, it would take forever. So doing all of that was really helpful for them in efficiency wise. Realism is another big one, especially when integrating with live action film. This is the case that you're going to use the attributes of our physics, of our, gravity, so that these simulations blend in with our real life. So it's difficult to do this by hand. So this is the best way to get a realistic simulation that emulates the motions of nature. So I'll show this little simulation in a second to express, how particles can move. But another way that this is great, like I said earlier, being inventive, is exaggeration and appeal. So for entertainment purposes, you can create really cartoony effects like Merida's hair. The springs are not affected by the normal gravitational pull that we would be experiencing. They have their own gravity. So this helps for film, for other entertainment purposes, to really give things life, to align with the characters that you're creating and things like that. So it's not always to be realistic. It could be used in the exact opposite way just as effectively. So this is a little simulation here I'm going to show with water. A lot of them, it's hard to understand because you're literally just seeing water. These are larger chunks of particles that you can actually see each sphere, and they're set to their own equations. You can see how they interact with the actual bounding box of this simulation here. So that's when it runs into it, and that collision there will cause them to bounce backwards. So they're all set to the same equation that makes them interact like particles of water would. So on the scale of an actual film or any other simulation of special effects, those particles would be much smaller and they would blend together to look like water. But that just helps understand, like, on a larger scale, what we're talking about with particles. Okay, so did I skip something? No. Now I'm going to be talking about character effects. So character effects are a little bit different because they have to follow the mesh, is also the geometry of the character. So we're not only interacting with the wind, the gravity, the other forces that are happening in your scene. You actually have to follow the character, interact with the character, and things like that. So they often need to be exaggerated, or it will or have their own environment for appeal purposes, like I mentioned earlier. So this is just a short little thing with some springs from Merida's hair. You can see the different sections here, but they'll play a simulation where it's not on its, doesn't have the support strings that I'll mention. So here's the normal one. This is what it looks like in the film. It's bouncy, it follows her. And then here's it with normal gravity. It doesn't, have that shape. It doesn't move with her. This here shows it goes a little crazy. So these effects are used in other ways that really complement the characters and can find, better ways to represent realistic effects. So here is a breakdown of a simplistic version of her curl. So what you would do in the case of creating a simple simulation, which is I'll be doing later, and with the curly hair, is we're going to break it down into simple components. So rather than thinking of each individual string of hair or her whole head or the whole long piece, each segment of hair is going to be broken down into smaller segments. Because it's a curl, the springs work really well. So if you think about, so this would be her head here. This is just one curl coming off of her head. If you think of this lighter line as one curl, it would be a spiral. In 2D, it's just like this zigzag line. Each one of these segments is a spring. So they have spring properties in between them. And even with that was when it was dragging, and it still didn't have the ability to bounce back up. So it added these imaginary support strings. So these darker ones on the side, you can't actually see in the film or in any of the renders, but they do exist there. On the back side, there are these support strings that help bring the curl back to its original position, which gives it that life and that like bounciness of her hair. So they had to invent an additional support string, which is really super cool. In that case, it was something they hadn't tried before. But also, when you think about it, it all seems really complex. They're just simple spring mass systems. So in a real life production, so I have this system that they created, which is this one here that you can play with. You would be able to take those variables. There's plenty more to get the desired look and attributes that would make it look like hair. So that would be number of curls, number of segments, how long the segments are, the actual spring constant, so how like elastic those springs are, different things like that. And once you play around with it, you can combine it to create the hair that matches your character. So that's really where this becomes useful, because you can just plug in all of those. You have those variables. Something doesn't look right. Okay, let's make this a little bit smaller. Let's make this a little bit longer. And then you start to create those realistic looking hair pieces. And then when pieced together, it looks like that big giant curl. So on basic level, this is what it looks like. But realistically, it's the same spring mass system, just given those fancy attributes that make it look like hair. So here's going a little bit more into the math. So Hooke's law is just about the where the force of the spring goes, where it comes from, based on the spring constant and the displacement, the stretch or the compression of the spring. So in all cases of the simulations, what you're ultimately trying to solve for is the position of these vertices. So every one of those segments has the vertices on the edges. For the computer to execute these simulations, for it to print them onto the screen, it needs to know the position of where all those vertices are. So that's what we're going to be solving for always. So what you're looking for in this case with Hooke's law, with this equation here, is the displacement of where that spring is going to go. So you can calculate the position if you're considering all of the other forces that you have on those particles. So here I'm assuming that the environment has some kind of net force, whether that be gravity or wind or her moving the particles if they have an initial position here, and then they would react to gravity in that way. If there were no net forces, everything would just sit still and this wouldn't matter as a simulation. So if we're assuming that there's some net forces that you're placing on your simulation, you have that information. You know where those forces are coming from. You know how much they're going to affect those particles. So if you have that, you can then calculate what your velocity and acceleration of each particle would be from that force. In the case of the spring, using that spring, if you have a spring constant, you would set that on your springs. You can use the velocity equation. Velocity is the change in, like, the displacement over the change in time. In every case of a simulation, you're starting your time. So when you run a simulation, you have a clock running. Everything has that value of time as a variable. So you know how much time has passed. You know how much it's moved because of the other forces that you've placed on your particle. This would yield the displacement of the particle, and then that's how the computer would know where to display this object. So again, this is too taxing for a human to calculate for every single vertice on every vertex on every single piece of hair. Oh, you have a question? Yeah.
Gina, do you know how many little pieces of hair does she have
I
in that
don't.
specific? Because
I
I assume it's thousands.
Yes, it has to be. See no hard edges.
No,
I have another example later on with clothing, where it's showing the subdivisions, the difference between something that is low poly compared to how many, multiple subdivisions, how more realistic it looks, with many more vertices in the. So in that case, obviously it didn't look like a real curl because we're only dealing with 6 points. But then, like you mentioned, I have no idea how many segments there are. Yeah, it must be thousands. And that's how they get the look where you're not seeing any hard edges at all. So yeah, pretty cool. But this is one of the factors in calculating where those points are, what the computer's doing on its end. So now I'm going to go into clothing. So why this is different from hair is that the pieces of hair work as a chain. So they're just working this way. The clothing is now like a web or a map. And so each vertex is relying on all of its surrounding vertices. So if your clothing has some kind of stretch to it, also if it has springs, we're dealing with all of those forces around where it's going to move. So it's a lot of calculating. So this is the one I was talking about with the subdivisions, but when you're running each simulation, of course, we're looking for where each vertex is. So we're trying to, consider all of the equations that might be working on it. So in this case, we're going to see gravity. The shirt is placed at initial position, kind of out, so that we can see how the simulation is going to affect it when it's pulled down. But then now, since it's a web, we're looking more into the relationships to the other vertices, which is really what makes the clothing simulation. Also here we're seeing some collision with the human model. So this is going to affect the position of those vertices. The human model is rigid. So once the point from the clothing hits the skin, it's going to stop. So that's when it drapes. It can drape over the body, and that's what makes it look like clothing, which is super cool. They've programmed that once you hit this rigid object, you're going to stop. There's a collision there. So and then also we're seeing the effect from the initially assigned position in the 3D space. So this is super cool. The first simulation that they show really quickly has much larger faces. So there's a lot less vertices that they're dealing with here. That can be helpful if you're looking for something that can be done quickly, not using as much computing power. But the more subdivisions that you add, so the more vertices that you're going to do detailed, this is the more accurate that the simulation is going to be. But again, the more taxing on your system. So here's a little bit more low poly. It still looks good. It's still interacting. But then by this last one, we're seeing an extra subdivision there, and it is very realistic, the simulation. So it's super cool to see how much that's affected by it. But that's just a simple clothing simulation there, how it's hugging and wrapping around the skin, and how those subdivisions can affect it. Um, so this is what I will be doing. I'm simulating a curtain with particles. Very simple, very basic. So what I'm considering, in addition to the spring mass system from the hair, because it's still a chain, I'm not using support strings like the hair case, but I will now be considering collision. So in my simulation, these beads are interacting with each other, but they're also interacting with an object that I have moved through. I have my little character walking through this curtain. Um, but when you're creating something like this, you have to consider, the mass of each bead. So that's how they're going to pull each other in each direction. That's how gravity is going to affect them, and then affect the one above it and the one above it. So also each bead is connected by a spring here. So it's almost the same as the hair simulation. Why I considered it almost cloth like is because the curtain by nature from hanging seems a little bit more cloth like. I'll show how you can expand that later to be more realistic. But what I'm ignoring in my case, because it's simple, is the web or the mesh of clothing. So I'm not having it interact with the ones around it, surrounding it. Each string of beads is individual on its own. If it runs into the other ones, it will react, but they're not connected on the bottom, and they can move individually. So yes, for the purpose of this simulation, I'm returning back to the individual chains rather than the web. That was a bit complicated. So my goals here is creating a believable simulated motion. So in some of the examples previously shown, attributes have been assigned to the particle. So that's what really, you can really tell it looks like water. It really looks like hair. Here, I'm just trying to simulate believable motion, not a believable, simulation. So it doesn't look like really anything other than some gray balls hanging in space. But if they were assigned attributes, they could look more like even a bead curtain itself. If you had textures to look like clay, different colors, things like that, then it would look more realistic. So another thing that I'm trying to achieve here is the interactivity and collision. This one was okay. I have simulated the relationships between the particles themselves, but really what I was trying to accomplish was the interactivity with the character, which was not so great. It works a little bit, but it goes kind of crazy. So I'll show you that, but I think I have a little bit of the math first. So that's what I was trying to do. But when we're considering the collision, we have to think about Newton's third law of motion. So upon the collision of these two objects, the force that they're putting against each other is going to be reversed back. So it seems simple. What we give in, we get out, but not always, because then there can be other forces working on the system. But also in the case of these 3D objects, they are not always going to hit perpendicular. So if you're thinking in a 2D plane, okay, if we're here, we're just going to go like this. Well, sometimes in this case in 3D, we're hitting here, we're hitting there on all different angles. So it's a lot more to deal with. It's a lot more to calculate. And then again with the interaction with the character on the collision, we're trying to detect when each one of these particles touches a vertex on the character walking through it. So then this equation will be employed when it says, oh, okay, I touched this character, I have to now move out. Well, my simulation took that a little too seriously. As soon as it touches the character, they just like fly away. I don't know why, but it's it's complicated. It is very hard subject to grasp. But so that those are some variables that you also have to consider when thinking about collision. So here's the equation that I'm using to think about the angles. So because we're not moving just completely perpendicular to each other, this equation is just for one plane. So this has to be over x, y, and z. Um, the mass of the objects, so what the two objects you're using, all of mine are the same, they're all the same bead. And then the initial velocities, so that could be where they're coming from the last collision, from being interacted by the actual character, things like that. What we're trying to find is this the v prime 1, v prime 2, or the subsequent velocity. So that's what the um, computer is concerned with. Where is this going to go next? So we're trying to calculate, okay, so we know where it's coming from, we know the velocity, we know how much, this mass, we know where it's coming from, where is it going. So we have these angles, they're just adjacent to a relative perpendicular axis from where they're going to collide. So we're seeing this theta 1 and theta 2. These are the angles from which these are coming to interact with each other. Those are going to help us calculate where is this going to go next. So they might not just do that. They have to, go crazy ways, as you will see. So that would be over x, y, and z. So it has a lot to calculate for each one of these, each vertex as well. So you're giving the program initial positions, mass, and velocities for these objects. So it knows where they're existing. So this equation here is used to calculate the resulting forces and the resulting angle of where it's going to be moving next. So here's my simulation. So they're reacting well to each other and they are simulating gravity. So if you wait till after the character moves through, there are some points where it does look pretty realistic. The bead curtain becomes less believable when the character encounters it. That is also because this bounding box is not, completely flush with the surface of the character. It's more of a dome-like, bounding box. So it doesn't look
Like
extremely
an
accurate.
aura, like a square,
Yes,
like a
exactly.
cubic
It's like
aura
I
around
can't
it.
come anywhere near this character.
Mhm.
But the collision was interacting with way too many vertices at the same time, and it was overwhelming the simulation a little bit. My computer crashed many times. So that's why the bead curtain is only like 4 wide and 8 long, because it was too many before and it crashed and whatever. So this is the simulation. So this is the character. That's the bead curtain. And when he hits it, they go crazy. Yes. But then here we're seeing, okay, now we're interacting with just each other and gravity and these springs, and it starts to look like what a bead curtain would look like if it was, floating in space. So he's initiating those insane, forces in the beginning, but then after that, it starts to, okay, I understand where I'm going now. So that's me interacting with, the character I'm playing this thing, but it looks about right. It's just when it collides, it's not so great. But yeah, so that is my simulation. So how you would expand this from my simple version. So like we talked about earlier with the Merida simulation, so we just had that little 2D graphic. How that turned into her big head of hair is expanding this would be creating that mesh. So this is a mesh here, the topology of like what this clothing would do, what it would look like. So instead of those beads being single like this, they would, each one of those spheres would be a vertex. So in this case, they're, the connections between those little triangulated faces there, but they would each be interacting with each other. They would all be connected. So it would be that on a tiny little scale, but a lot of them all together to make it look really realistic. So of course, I don't have the computing power for that. It's amazing what can be achieved with this. So similarly, if my bead curtain had been connected, it would have looked like a sheet of like a cloth hanging, from a. Oh yes, question.
It's an important question because you keep
Mm-hmm.
talking about you not having the adequate computing power to do this. So this is actually very important not only for the mathematical programming department but also for the animation major and for our department. What type of equipment would you need to actually be able to do this?
Well, you would need a very large short-term memory on your computer. Mine is 8 GB and it cannot compute that much and store.
No,
So what it's doing is it's storing these values like instantaneously, and it's like re-recording over these values over each other
no.
millions on a time.
So you
And
need something that's going to be at least 32 to 64, which is gigantic.
yeah,
And ideally, it should be a PC because it runs faster, or a
yeah,
Mac.
gaming computers, things like that. Yeah, things that can
Okay.
compute very quickly. Mine was, the fan was going. it
Oh,
was it was
I know
struggling.
that feeling. I
Yeah,
know that feeling is like.
yeah.
I actually have a little thing that cools it down underneath and know that. Yeah.
I should get that.
Hmm.
Yeah. So yeah, definitely computing power is very important. So here is an instance where there's unlimited computing power. This is from Pixar. This is a simulation that they did from Coco. So it's something that we see and we definitely take for granted. I think it's beautiful in the film, but then when you really, I mean, looking at how difficult it was to make this series of bead curtain, these skirts are amazing. Each one of those skirts, they're obviously made up of their own mesh, but they're also reflective. They have all these other properties that make them look this like silk, the way that they're interacting with the actual character with the layers of cloth below it. It's outstanding. It's amazing how this can happen from the basics that I just laid out. So that was the clothing simulation. I believe that is it. Yeah. Oh, I have one last one that you actually showed me that was coded for web. This one is really cool because there's wind here. And then you can put this sphere in it to see how it reacts around the sphere with the wind, which is also really cool. Just wanted to add that at the end as another very simple. This is more of what mine would have looked like if obviously the beads were smaller and connected throughout. So if it was a web rather than chains or links of the springs. So yes, that is my simulation. Thank you.
Very good presentation. This is going to be great.
Thank you.
I'm going to be getting the form and I'm going to be sending you an email very soon. It's actually not a complicated process, and I'll let you know what it is. But I think it's very important that we start archiving
It,
these projects.
it takes just a minute. In fact, it's a form that you end up submitting as a faculty through Submittable, I want to say.
Yeah.
Okay.
Yep.
Yeah, I just did it for honors thesis, so no big
Yeah.
deal. Yeah, Gina, this is really great. I mean, I'm so happy to see you're sort of connecting the math here, and I am much more on I'm on the geometry side of the math spectrum. Your forte is and sometimes completely alien to me. So
Mhm.
it's nice to get a very clear view of kind of what's going on under the hood in the machines, and also it speaks to like even the basics of what we started talking about in like 211, where it's like the idea of calculations and computers and computing power and sort of what can be imagined through the technology, what can be envisioned through the innovations in all these technologies, right? So it's definitely really it's fitting for you to do a project like this, because it really does sort of align not only both majors, but also really like at its core, like
Yeah.
what animation relies upon centrally in terms of like everything from like Newton and the Renaissance math, Leibniz and calculus all the way to present in this way that's really it's like clear headed and concise and not overly complex. Like for somebody like myself who's not deep in the math, like I can, again, mathematical logic, I'm okay. You get me into like pure math and it gets a little bit, it's out of my range. So it's nice to have it distilled in a way that rarely is. And also it's true that we're looking at all this stuff that's like, they just probably just the computer did it. But in fact, there's so much to think
Right.
about when
Exactly.
these things are being set up.
And
Yeah.
on my
Oh, it
side, I
is.
absolutely love the math. Don't give me logic, give
Yeah,
me.
we
And
know
one of the things
that.
to understand is that we have to realize that animation goes beyond nature. We don't have to simulate. We can create our own rules. We can create our own environments, our own laws of physics, and then we can go beyond. And probably by doing that, we're going to be able to understand better how the restrictions of real physics are. When we break them, when we say it doesn't really matter if negative is if the gravity is negative, well, they're all going to start flying all over the place. And so let's play with that, and that way we will be able to understand. And I wanted to mention also, you started playing already with these, as I call them, particles or objects. You started playing with those in your game, rescuing the fallen
Oh,
cheerleaders.
yeah.
It's
Love it.
exactly that. In a very basic format, they were either alive or dead. It's like they're like, so it's either, but that's a very, very basic introduction to what we're doing. It's tying in completely both majors and seeing how is it that they both connect. So I think it's a fantastic presentation.
Thank you.
Yeah, definitely.
Yep.
Definitely.
I
Yeah,
will
I
be
think that,
sending you the form very soon. It's very easy. I will be signing it. It's just that. And then what we're going to use is I'm going to need a copy of your PowerPoint presentation. If you can
Absolutely.
share it on Dropbox, and
yeah,
then we will submit that to the library. So it's going to be in the repository of the library.
yeah, there's no need to, that was an Unreal project with that,
Mhm.
yeah, with that piece of the fabric in there, or the bead curtain. Yeah, there's no need to like submit that build. You just need to give them the presentation. The PDF is enough,
Yeah.
or
No,
a
the
PDF,
PowerPoint. PowerPoint.
PowerPoint or a PDF, however you
Yeah.
want to do it.
Because the
Probably,
PowerPoint contains the movies, and that way we can.
yeah, that's better. Are they, and they're embedded movies? Or are they linked out to the
Uh,
web?
a lot of them I linked, they're from my Google Drive. So I'd have
So
to,
they should be embedded. So try to embed them,
Yeah,
and
yeah,
that's it.
and make sure to embed them, because otherwise, if the links change, those will be no good,
Yeah.
going forward.
Yeah.
You want concrete kind of hard links. So
But this was a great presentation.
yeah, it's actually the first one I've seen from math, and it's like so refreshing in a way. It's
It
like,
is,
wow.
it's fun. And then we hope we're going to get more. It would be great to have more animation in new
yeah,
media and everything. And then now that we have the computer science too, all these connection between mathematical programming, computer science, new media, animation, and is going
Yeah,
to be an ideal ground for creation.
yeah. They're all
yeah,
pretty fun to watch because all of us have like separate interests other than math. My
Yeah.
last two roommates were math majors, and one of them was on the rowing team, and the other one, her other major was bio, and she was studying animals. So she did hers on population systems of animal that was going extinct, and my other roommate did hers on the perfect rowing stroke. So it was like they're still very personalized presentations, but it was, all the math about both of them, and it was super interesting.
I
So
love
that's
that.
really
And
good.
that's why you're in college to see
right.
people who are completely different but share same passions. Cool.
So
So
true.
this was great, Gina. I'm going to stop the meeting. Thank you so much.
Yeah, and
I'm
I
going to
think
be
I'll see you in
sending.
a few.
Yeah,
Yeah.
and I'll be there in 15 minutes. Yeah, I'm going to be filling up the
Okay.
form. I'll send it to you.
Okay.
I'm going to stop recording right now.
Okay.
And
Okay.